Hi, can you hear me okay?
You can start when you're ready. Okay. Thank you.
Okay, so thank you. Thanks everyone for your resilience coming back. So a very interesting talk by Yuta on compact stars. And now what I want to do is I want to continue from where I started yesterday. So yesterday I spoke mainly about some of the theoretical foundations of teleparallel gravity. And I just, before starting what I had planned for today, I just wanted to talk about 2 points that came up in the question session. First was the Bianchi identities and then the geodesic equation, because it's very important to understand this. So, in the first case, the Bianchi identities, so what are we doing? We're switching from the Riemann tensor as a measure of curvature to a torsion tensor, which is a measure of torsion. So we're doing this by changing our connection. And in the slide, the way I denote this is, so gamma here would be our Levy-Civita connection, and gamma with the dot on it, as you can see on the right-hand side, would be our teleparallel connection, for instance. And since the torsion tensor has 3 indices, so things change slightly, but not drastically. There's a lot of superficial changes, but not so much in terms of how we view the Bianchi identities. And by this, what I mean is that we continue to retain both these Bianchi identities. So the first one just being, as you can see in the first point, I change from this in the brackets. You can see what we have from GR, what we know from the Riemann tensor, and how this changes, and how we add another index to the torsion tensor through derivative terms. Now there are some details of this covariant derivative here. It's a covariant derivative with respect to the teleparallel connection. However, let's not get too bogged down in that detail. And for the second Bianchi identity, again, we get something very similar to what we have for the Levy-Civita connection. Here, instead of R, now, okay, we don't have T, we have this Q, what I'm calling Q, which is some complicated function of this teleparallel connection. It's a function of that. In the end, it can be shown that this does give us conservation of energy, but I just wanted to show these 2 Bianchi identities to show that, we still retain some semblance of our regular view of gravity, let's say. And then in the last point at the bottom, I just wanted to compare the 2 geodesic equations that we have from generativity and then also from teleparallel gravity. So in generativity, okay, as we know very well, that we have geodesics coming with no force term on the right-hand side. Whereas in teleparallel gravity, we get we get the same geodesics, and we see this through the equation in the brackets, where I compare the 2 connections with this K, and this K we call a contortion tensor. I don't want to say so much about that, but it's just a function of I mean, it's the difference between these connections at the fundamental level, but it can also be expressed as through the torsion tensors if we want. And in any case, over here again, on the left-hand side, we get the geodesic equation, fine, but we have now a force term on the right-hand side. So while we keep the same concept or the same, let's say, the same actual geodesics that happen in reality, now the way that we view them in the theory, in the foundations, is different, because now we have a force-like term coming into this. So again, I just want to sort of put those 2 points, let's say, into equations, so we can see that. And also, just we've been talking very much about Horndeski gravity, and I just want to say something also about Horndeski gravity in teleparallel gravity, or how Horndeski gravity can be realized in teleparallel gravity. So, as virtually every presentation has mentioned, so Horndeski gravity. In Horndeski gravity, we have 1 scalar field. It gives us general second order field equations. And in a lot of the presentations, we also saw this action with these Lagrangian terms. So quite messy, but it does give us the most general second order theory with one scalar field. In what we can call standard gravity. By standard gravity, we can take that to mean gravity based on curvature, on the Levi-Civita connection. Now, the question that we had some time ago was, what would this look like in teleparallel gravity? What do we need to do to try and find a similar setup as Horndeski theory, but in teleparallel gravity? And since teleparallel gravity, as we mentioned yesterday, since it is organically lower order, so what I mean is that because if you recall, the boundary term is sort of separated from our Einstein-Hilbert or our teleparallel equivalent of generativity, TEGR action. We're allowed to create a much wider zoo, in a sense, of lower order theories. So in this case, we're thinking about second order theories. And the big difference here is that actually we need to put in more conditions so that we can constrain how high order these terms can be. So meaning how many new things do we get in this theory? So that would be our second we have our first condition, being that we still want second order theories. As a second condition, something that we put into this is that we don't want parity violating terms. You know, at first glance, you wouldn't want these things, at least at your first stab at the teleparallel Horndeski theory. And what I was saying earlier comes into our third point here, which is that we limit ourselves to having quadratic contractions of the torsion tensor. And this is important because I can take infinite contractions, and that may still give me second order equations of motion, or that will still give me second order equations of motion. And in this paper, we talk about how this paper at the bottom that I refer to, we talk about how that would actually be conceptualized. And what we say there is that essentially that we keep all the standard gravity terms. So this L2 to L5, these complicated terms. Okay, they look different. They're calculated in a different way because we're dealing with the teleparallel connection. But because of many of the equivalences, we get the same things, the same field equations in the end. But now we also get a new term, which we call L tele. And in this, okay, we get phi and x, the kinetic term of the scalar field. But now we get three terms related with the torsion tensor. But very importantly, now we get this so-called I2 and JI, which are new terms, which have an important relation, which are important scalars because they're more matter coupling scalars, terms coming into our theory. So like this, we sort of expand the breadth of our Horndeski theory, or what we can call TeleDeski. And I just want to say one point about gravitational waves. So again, Tessa spoke a lot about this wave equation up here in the box, where this is sort of our general wave equation, okay, without a source term, but general in the sense that I'm not assuming a specific theory. Alpha M and alpha T can be the parameterization of my modified gravity in a certain sense. And what we did in this paper that I refer to at the bottom is that we take tensor perturbations in a cosmological background, and what we're looking at is to try and determine these alpha T and alpha M, so our TeleDeski, our teleparallel analog of Horndeski theory. Keeping in mind that we have extra terms now. So in black, we get the standard terms. And most importantly, for alpha T, we get these first 3-4 terms related with G4 and G5. And the multi-messenger constraint, which limits this alpha T to being 0, has severely constrained these terms, which is why the space of Horndeski theories has been so constrained in standard gravity or curvature-based theories of gravity. But what we find in our case is that we get these two extra terms, that depend on derivatives with respect to J8 and J5, but let's not get into those details. The important thing is that this new term, this G teller, gives us a way to evade problem, because in standard gravity, okay, once you choose G4 and G5, you're going to have problems. So like this, we can, in a sense, solve this as a differential equation and come up with a wider variety of Horndeski theories. So this is one proposal, one possibility of ways to revive Horndeski theory in a certain sense. So I just want to talk about that a little bit. On this, it's still early days in the sense that there aren't so many works, since it's a relatively new model. But it's interesting in that it gives many, with so many works in standard gravity on Horndeski theory, it's worthwhile maybe to have a look at this. Okay, so now coming more to the observation side of things. Now, mainly in teleparallel gravity, most cosmology and even for solar system and galaxies, most works have been in f of t gravity, but there are some in f of tb, and there's a growing number in f of tb, so there's a lot of promise there as well. And just to remember a little bit, so these are our actions for f of t and f of tb, and to remember a little bit, T and B give us, combined together, they give us the Ricci scalar, as you can see the box at the bottom. So for flat FLRW, for instance, I mean, in all cases, the Ricci scalar is equal to minus T plus B. But for flat FLRW, you can see through a one-liner calculation how these things can be combined to give us the standard Ricci scalar. So to get that, so we have two ways of looking at this. Also, just to remember a little bit, to remind people a little bit, so f of t. So first of all, in both cases, we're looking at f of t and f of tb as an extension to TEGR, an extension to standard gravity in red here. And secondly, f of t is generically second order, which is an uncommon thing in modified theories of gravity, because the Ricci scalar, if I take something like f of r, if I'm only dealing with gravitational scalars like the Ricci scalar, I get fourth order field equations, which I do get for f of tb, but that I don't get for f of t. Again, going back to that this, for many reasons, this is an organically lower order way of constructing gravitational models. So the first thing we ask ourselves always is, what happens in solar system, in the sense, we're not going to get so many tight constraints from solar system, but solar system can kill a theory. So we must make sure that in solar system, through some of these tests, and there are some more, that we're well behaved, that our model of gravity doesn't go wonky, and we may get nice cosmology, but then our solar system goes off in a certain sense. So fixing one thing and sacrificing something that is a very big important thing. Okay, so again, not to go equation by equation, but just to mention a little bit. So for solar system, we can look at solar system through PPN, or in this case, in the study that I'm mentioning here, we're looking at it through actually calculating some of the tests that we have. In this case, so as you can see the difference here between the black and the red text or terms in these equations for various terms, from perihelion precession to gravitational redshift. And in this case, we're looking at the power law for f of t. And okay, you can see how the terms would arise. So it is the case that, at least in the case of f of t for power law, that this does have an impact at solar system scales, in the sense that it doesn't just disappear, but as you can see in the last point, the effect, at least the constraints we get from solar system, give us, okay, in this case, this alpha term to be less than of the order of 10 to the minus 4. So not so much of an impact coming from there. And what we want to do is we want to see how this compares with other things as well. Something else that has been done quite recently is f of tb, solar system test in f of tb. In this case, okay, so we're trying to see a little bit more generally what's going on. So now you have two scalars. Automatically, when you have two scalars, in this case t and b, your theory, okay, you have a choice in what you're going to look at. In this case, we try to look at as general a situation as possible for the contribution, a sort of power law contribution for various combinations of the torsion scale and the boundary term. And so in this case, again, this isn't all of f of TB, so there's still room to do other things. But in this case, which is still quite a general case, what we see is, okay, we don't get a general solution in a certain sense. And this we would expect. We would expect firstly because it's quite a complicated theory in a certain sense, because we have two gravitational scalars, but also because f of TB branches out quite a bit. As we saw yesterday, we saw this with the scalar perturbations, where we ended up with 4 cases going on over there, or 4 branches. So in this case, we would expect this to break up a little bit. And okay, and there's a whole data overload here. However, without going through all the particulars of this, one thing that we can do is we can go through all those cases, but for each case, we can look at all these different kinds of solar system tests and try and get constraints on these different parameters. So one thing about this model, as I said, it's a bit complex, but also it gives us a lot of free parameters. And what we see is that, okay, it's not the same parameters all the time for all the, well, it's the same parameters for the different tests, but for the different cases, we get different parameters. So it gives us, in a sense, certain options when we're trying to say, okay, what works cosmologically or on the galactic scale physics, and how can we compare this with what's going on at solar system, for instance. Something else, so going up in scale is a little bit something else we can look at, which was looked at in this paper down here, is what happens at galactic scales. Now, this really hasn't been a lot of work on, but just to give one example, I mean, the only example of a study. So for galactic scale, so in this sense, we're looking at specific galaxies and trying to very straightforwardly match up the rotation curves. So, okay, breaking up a galaxy into its like spherical bulge center part and the disk, the outer region, through these, okay, brightness distributions, whatever, there's a lot of math that goes into it. But in the end, we can get velocity profiles. And what's very good is that we can use those velocity profiles to constrain these parameters. So again, looking at, in this case, at the power law with alpha and n. And okay, so so on the left-hand side, we can see the Milky Way. And in that case, okay, if we're looking at GR without dark matter and red, it doesn't work. We need dark matter to make GR work, hence lambda ACDM. However, for f of t, in this case, for certain parameters, it does seem to work in a certain sense. But again, very preliminary studies, and on the right-hand side, we have some other examples of different kinds of galaxies that have this discompose characteristic. So galaxies, it seems, may not be so bad either. But what about cosmology? Moving on into cosmology. So again, so yesterday we mentioned 3 models: the power law, Linder, and exponential models. In cosmology, we can relate. So in all cases, okay, we have an alpha, and then we have a power, p, in this case, p. This p changes, sometimes it's p, sometimes it's b, depending on the authors or the studies that are going on. But by evaluating the Friedman equations at current times, we can actually relate these alphas to p. So as you can see at the bottom over there, so we don't really need to think anymore so much about the alphas. And what I want to talk about here is this study done by Xu et al. And what they did was they compared, okay, they took, just move this. So they took certain combinations of data from surveys. So in yellow supernovae, and then going on to both BAO and expansion Hubble data. And what we want to see is, okay, here on the right-hand side, we have the situation for lambda CDM. Okay, or parameters as we would expect them to be. Also, they assumed in some cases, like in yellow, they assumed this Reese prior, so a very high value of the H0 Hubble parameter. And something else to say over there is that when we put in BAO is basically all of them except for the yellow one, that this has an effect of reducing the H0 and omega matter at current times, which you would expect because BAO, as was mentioned yesterday, very importantly, BAO does have a dependence on lambda CDM, and lambda CDM does predict lower values of these parameters, especially H0. It depends on lambda CDM as a fiducial model, and there was quite a discussion yesterday about this, so I won't say so much, but it's not totally model independent data in that sense. Now, okay, just to go through these three models very quickly. So if we take the power law, the F1 model, again, on the right-hand side, I was keeping lambda CDM. On the right-hand side, we can see what we can say. I mean, again, alpha 1 does depend on P, so it's not really a free parameter. But we can see a little bit about what happens for P. So for the base case of just supernovae data and H0, we don't have so much constraint on this P parameter. But in the other cases, we do get a tightening, a restriction of this constraint. And in all cases, it's not exactly centered at 0. And what 0 would represent for us is lambda CDM, because even if you look at F1, that this would become a constant. Again, f of t, or later on f of tb, is sort of the extension of TEGR or GR, if you like, which for lambda CDM is just a constant. So in the other cases, we get something similar in the sense that for just supernovae with a H0 prior, with the Reese H0 prior, for P, so that would be this lower box down here, we don't get so much tight constraints. We need data points at higher values of Z, which is what BAO gives us. And then in these cases, then you get this becoming more restricted. In this case, it's not so obvious from looking at the model F2, but P equals 0 again gives us lambda CDM because of the shape of alpha 2. So because you get 0 and 0 in a certain sense. But again, so lambda CDM here would be represented by P equals to 0. And also, as we would expect in the last case. So again, so P equals to 0 gives us lambda CDM. And again, in all of these cases, okay, we're still in the neighborhood, as we haven't found modified gravity. So we would expect to still be in the neighborhood of P equals to 0 for our P parameter. But there is some hope in a certain sense that it's not totally constrained to being 0 in a certain sense. And maybe just to mention something interesting that we've been working on this year is to try and think a little bit about not just selecting specific models of F, or in this case, F of t, but also to try and work backwards to try and generate an F of t in a certain sense. I mean, here, this is sort of the beginning of that. But one thing that would be very interesting would be to see this through to the end in a certain sense and really try and take a very general approach where you really generate, in this case, an F of t or a modified gravity model where that is the result rather than you selecting a priori your models in this case or in the case before, and those three, the power, linear, and exponential models. So this would be the remit of machine learning, and there's a lot of interesting things happening over here, but it's a very new topic. What we're going to talk about here is something called Gaussian processes. So Gaussian processes gives us a nice way of sort of getting rid of certain noise in data, or a nice way of smoothing out data. And the way this works is that, so in this case, you still have your data points and all of that, but what you want to do is you want to now sort of try and, what we want to do is, first of all, we want to do this Gaussian processes business. And then from there, on top of that, we want to build an F of t. But first, there's a few bits and pieces on how we do this and what we get as results. So a lot of things related to hyperparameter, deceleration parameter, and that sort of stuff. So in this case, we're assuming that each of these points, in a certain sense, is like part of a Gaussian on its own. And in this idea of Gaussian processes, which as a figure would be the one on the top on the far right, this would be what we'd want is we'd want a way to relate these different Gaussian functions together. And we do this through something called a covariance function or kernel. And what this would do is this would, in a sense, that's our model now. And it would have some parameters, but these are not physical parameters anymore. So hence the model independence. But what we want to do is we want to then either take a Bayesian inference approach or something else, whatever you want to do, but to again constrain those parameters and try and learn a bit more about how to smoothen out this data in a certain sense. And I said that we need these kernels or covariance functions. Here are the four most popular, let's say, the square exponential at the top left being the most popular because it's the most applicable or the most general, and you would expect this, it's a Gaussian basically. And the reason why I'm showing four is because one thing that we did in the study is we wanted to understand, really how are there any changes between these kernel functions or these covariance functions. And in the study, what we did is we took, on top of this, we took the four most prominent or important H0 priors. So the model independent values of H0. And when I say model independent, I mean independent of cosmological models. So as we all know, the Planck collaboration have this these are not, sorry, I said that they're model independent. The Planck value is not model independent, as we said quite a few times yesterday. It's the others that would be independent of a cosmological model. But for the Planck prior, so we get a very low value where this depends on lambda CDM, and it comes from the CMB data. The next one being the shoes or the Rees prior. So in this case, they get the highest value of H0, so 74, in this case, 74.03. On top of that, then there are two other important ones. So the third one being the tip of the red giant branch. So this means, looking at that Russell Hertzsprung graph of stars, basically. And in this case, looking at a very important turning point, the tip of the red giant branch. And that team by Friedman et al. Got a sort of value right in the middle between the Planck and Shoes numbers. And something we mentioned yesterday, the whole Licau number is sort of on the far end next to the Shoes prior at a very high value over there. Something else we want to do is from the H0s that we're going to get out from these Gaussian processes, want to compare these with the priors that we're looking at over here. And so that's with this D argument at the bottom. The only real thing is that this obviously comes out, we're looking at it, gives us, it's like a distance function, but in units of sigma. So it's very nice for that reason. But anyway, okay, our data, what we care about. So we look at CC data. Okay, so the blue line here would be our lambda CDM line. And on the top left, we'd have this, you can see a lot of CC data and also some supernovae data. On top of that, in the study, we do use a little bit of, we use some data of BAO, which again has a fiducial model dependence on lambda CDM. And just to move on a little bit. So what we want to do with this is we want to work our Gaussian processes on these points and to see if we get with how far we deviate from lambda CDM. So in all of these cases, we're looking at lambda CDM. These graphs are a little bit busy, but you can see lambda CDM as a dashed black line. And in these cases, the colors correspond to blue being just cosmic chronometers, CC, and green being cosmic chronometers and supernovae data, and the yellowish line being that, but with CC cosmic chronometers with supernovae and BAO. So the one thing that we see over here is, so on the top left, we're seeing the situation with no priors. Whereas in the other cases, so on the top right, we're seeing the biggest prior, the Rees prior, and then at the bottom, So again, on the right-hand side, we're seeing the one in the middle with TRGB, and then on the left, we're seeing the holy cow prior. And as you would expect, since the Reese prior is so far away from the, let's say, the lambda CDM or the Planck value, that we get very large error bars. I mean, in blue, you can see a lot of that. You can see that the error bars grow with redshift, with Z on the x-axis. You would expect this because the CC data is very much more towards Z equals to 0, let's say. And then the Reese prior, it being so large, gives us the largest errors in all cases. Now, just to try and save some time, going onwards a little bit. So this is the same thing, but with the Cauchy kernel. And again, just for illustrative purposes, to see that we get roughly the same thing in a certain sense with very small differences. But what's important for us is to try and see, firstly, see what values of H0 do we get. And okay, a lot of outputs, a lot of results on this, but just in bold, there we can see the smallest and largest values, the smallest being where we add with no prompt, and then the highest one being just cosmic chronometers with the Reese prior over there. And this is with the square exponential. And then with the Cauchy, roughly, we get, within reasonable uncertainties, we get the same thing for the Cauchy situation. Something else we did is we looked at something called diagnostic tests to see how we can test lambda CDM using this approach. So at the top, we have the Friedmann equation for a dark fluid. And the second point, so the very well-known Friedmann equation, let's say. In the second point, what we do there is we assume an equation of state which is -1, and we try and solve, again, we solve this for omega matter at current times, which now we call this OM function. And what we would expect, or what we would well, for lambda CDM, what we would find is that this is a constant, this is omega matter at current times, but we want to test that. So we take a derivative of that, we call that L1, and this is the diagnostic test, because this, as you would expect, would be 0 if we have lambda CDM. And what you can see here is, again, all the same combinations, 4 combinations of that data that we saw before with the different priors in the different boxes. And at 0, you can see the dashed black line giving us lambda CDM. And something interesting to see over here is on the top right, where we have the Reese prior, where if we don't consider BAO, so we don't consider the yellowish region, up to 1 and sometimes even 2 sigma at high Z values, so over Z equals 2, we do sort of deviate a little bit from lambda CDM in those areas. Again, this is very preliminary, and you need lots of work beyond this, but it is indicative that of considering modified gravity if we're trying to find arguments for modified gravity. Also, we look at the deceleration parameter, but just to make sure I finish on time, I won't talk about that too much. And something else we look at is the transition time. So when the universe went from deceleration to acceleration, and again, all the combinations of the kernels, and in bold looking at the smallest and highest values. The one thing to say here is that we get quite a range, looking at the different values. And also we look at the equation of state for this dark fluid. And over here, the error bars just shoot up very quickly for Z, roughly about 1 and sometimes even lower. So at least for this situation, this doesn't give us such great values, at least just in this particular regime. Anyway, moving on. So now that we have the GP stuff, one thing that we wanted, or that we wanted to do in this analysis was to try and work backwards. So to take a sort of finite element approach to this Friedmann equation. So trying to break up the terms in red and to get a numerical propagation equation, let's say, for the different Z values for this f of t. and we used sensor differencing. So together with this, one thing that we assumed is that at late times that we can take, let's say, lambda CDM to dominate at late times. And again, from the graphs that we saw before, at z equals to 0, this is a consistent way of looking at things. Then just looking at the Friedmann equation, we can take these two boundary conditions, so we can get a value for f at z close to 0. And from this, we can propagate out our f of t, and we can actually sort of cut out the middleman, this redshift, and just write f of t as a function of t. So this, in a sense, is a nice, interesting approach, I'd say, to trying to think about different Lagrangian models, because the problem with things like f of t is that you have such a large zoo of possible models that it's not so clear exactly what you should do. So things like this may at least be able to sort of guide us in the right direction of where to go. Again, over here, we've got this black dashed line in all the cases, and in these cases, that is our lambda CDM, and you expect it to be horizontal because f of t should be constant for lambda CDM. But what we see here is that also, some deviations from that, sometimes 1 sigma, sometimes outside the 2 sigma point, but mainly for the least prior on the upper right-hand side. So there's a lot of interesting things that maybe, or different directions that this can maybe go in. That's the square exponential. Similarly, we get the same general behavior for the Cauchy kernel. Going on from this, so going beyond background in a sense, so going beyond just Hubble data, something else we can do that we mentioned yesterday is scalar perturbations. And scalar perturbations give us this matter evolution equation in the bottom point, where we get a G effective. And with this G effective, okay, it's Newton's constant over 1 plus f derivative t. So for lambda CDM, we'd always get G effective for our regular situations, our G, Newton's constant of G for the regular situations, as you would expect. But anyway, so what we wanted to do so this is a different study. What we wanted to do was we wanted to have a look at this. And I only mentioned this data stuff because we use a lot of, we use cosmic chronometers, supernovae, fine. But also we use, as in one of the combinations, we use data about the variation of the fine structure constant. This is interesting because we can say some things about this G effective. We can sort of work backwards and try and see how this G effective works. And just to mention the results of this. So again, so in this case, we go back to assuming those 3 models of f of t. And in these cases, the blue regions are just us taking supernova and cosmic chronometers, which are model independent in terms of cosmology and a least prior. So very large uncertainties there, so we don't learn so much. And on the y-axis, what we're seeing is, okay, so this G effective on G minus 1. So we want to understand, where is this horizontal 0 line? So the dashed red line over there. In red, as the red region, then there we add this fine structure constant information. And there we do get some tighter constraints on this G effective. So we do get some more information there. So again, another way of thinking about this f of t stuff. Okay, sticking to the scalar perturbation, something else we can look at, which was mentioned a lot yesterday as well, is this parameter f sigma 8, which is related to the growth of structure, of large-scale structures. And here on the right, we have this now famous picture of how f sigma 8 varies with z. And all I really want to talk about here is a separate study. So in this case, this group here, you've got the citation at the bottom, they looked at f sigma 8 data, and what they wanted to do was, again, to look at those 3 models, so power law, Linder, and exponential, and to try and see what constraints we can get. So in this case, what we want to understand is, okay, do we agree at solar system? Do we agree at galactic? What about background cosmology? Now we're looking at perturbed cosmology. And in this case, okay, so not to go through the whole thing, but okay, so now the index, the power becomes b, and just looking at, okay, the third column over here, we see that, we do get a value, a non-zero value, preferred value of b, but b being 0, okay, it's still in the uncertainties, but there's a nice convergence, let's say, over here using this separate data. Anyway, so moving on a little bit. Now for the Linder, so again, this was done, the same analysis was done for the Linder model. In this case, not so much convergence, so I would view this more as work can still be done here to sort of understand a bit better what's going on for this F sigma 8 stuff, and similarly here for the power for the exponential model. Again, for B, we don't get such tight constraints. What else can we do? Well, so now we've seen a lot of F of T stuff, and that's representative of the literature, where there's a lot of studies in F of T cosmology in terms of observations and constraints from observations. But something else that we can look at is F of TB. So again, looking at the action, we can look at F of TB as an extension to TEGR in this situation. So as we showed yesterday, again showing here, we can work out the Friedmann equations from this. So in the second point, we can see the red being our sort of extensions, our exotic fluid. I think yesterday we wrote down the effective density and pressure, at least at background, what that looks like. These are all gravitational terms. And we can write down also an effective equation of state, an effective VOS for this. And what I want to talk about, just to tie it all together, is an analysis actually with Celia, where we looked at F of TB cosmology at background, and to try and what we wanted to do is we wanted to try and understand the viability of some of these models, to at least understand, okay, what behaviors do we get out, and what kind of values for these three parameters should we expect. So just to mention again from yesterday, we mentioned this so-called Taylor model, where we can take a Taylor expansion about background values of T and B. So when I say background values, so now we can say specifically, in this box on the top right, we have these sort of background values of what we mean by T naught and B naught. And we can make this huge expansion. The reason why we have to go up to so many terms is because B is linear. T in linear form is a boundary term. So it's, it doesn't contribute to dynamically to the field equations. So this whole thing can crunch down, and we can write in that last line over there. Maybe there should have been some more space there, but we can write it down in this very nice sort of power law form, not too dissimilar to the solar system case that we had a look at. And then at the bottom, what we're seeing is what happens now if we're looking at that equation of state. So do we, are we close to, to -1, which is what we need? We must get to -1. And in this case, okay, we're looking at specific situations with cosmic chronometer, supernova, and BAO data. But what we're trying to think about here is, do we cross -1? Do we cross the phantom line? Do we stay between 0 and -1 for a cross section of Zs? Okay, in this case, there are two different cases, and there's more details in the paper. But want to understand that, and in fact, we do stay over the phantom line. And something else is to understand how this varies in the middle with omega matter. So again, we stay roughly around the values that we would expect, so -1 and a good omega matter with the tallies up with observations. We had mentioned yesterday 3 models, so not just the Taylor model, but also a power law model. So it's just a straight power law model where B is a power law, and M is and B is a power law, and T is a power law. In this case, okay, there's a bigger combination of cases, and again, in most cases, we have something that looks that in general terms behaves as we would expect it to in certain cases, so that we do get -1 closer z equals to 0 by and large, let's say. Okay, this last case is a bit more exotic, let's say, but for the other two cases, we're in a good place in that sense. So again, looking at this against the data, against what those joint data sets. Again, so we can try and find values of these three parameters. And in this case, so here there's a lot of parameters, right? Because we have, in a sense, two power laws, right, going on over here. And in fact, this does give us reasonably well constraints, reasonably good constraints. So we can say so now what can we do? Now we can say something about these parameters from this analysis, as we can see here. We know that this makes sense because we get a H0 that tallies up with what we expect up to uncertainties. And now we can use this in other scenarios, other studies to compare what's going on. So something else, lastly, the last model that we can have a look at is our mixed power law. So now instead of just thinking about two separated power laws, now we can combine them together and just, okay, we reduce a little bit our three parameters. And again, look at this exotic or effective equation of state, this omega, this W. In this case, things are a little bit different. So in this case, in fact, in general, when there's coupling between B and T, when there are terms that couple these two things, we get a lot of exotic behavior, let's say. And this is interesting because keep in mind, so f of TB limits in a specific direction to f of r. So if the combination of T and B gives you a minus T plus B as an argument, that's f of r. So this needs to coincide with f of r in that setup. So in a sense, we're sort of taking f of r results and opening them up and looking at the sort of second order torsion scalar and the fourth order boundary term contributions and how that mix can vary things. And in any case, again, we can do the same thing and try and see how this varies against data. And okay, we get a reasonable value of H0, but also we get values, actually specific values for these coupling parameters. Yeah.
10 minutes left.
Very good. Well, I'm close to the end. We can have some questions. So yeah, so in this case, we can say something about the three parameters over there. And okay, so coincidentally at the end, so maybe can leave more time for questions if there are any. So just to round off everything that I've been saying in the yesterday and today. So teleparallel gravity gives us a sort of, we're not just extending generativity. We're not just taking what we had for generativity and adding more things to it, which may be the right way of doing things. But teleparallel gravity gives us a sort of novel way or a new foundational way of constructing theories of gravity. By changing the connection, we can sort of create a whole new zoo of modified theories of gravity. And teleparallel gravity does not have to be a modified theory of gravity. We do get TEGR, where I didn't mention so much, but we do get, well, obviously we can look at some of the issues in generativity, some of the theoretical issues. And one thing that we find in teleparallel gravity is that some of these issues can be sort of, either they go away or they can be revisited, and maybe we can find different solutions for these things. Also, observationally, there's a lot of interesting stuff happening, but we're still sort of at the beginning. So there's so many studies in other theories of gravity, and some of these were mentioned in the other presentations. Maybe sort of spending some time, spending some effort in teleparallel gravity can also give us some interesting studies, some interesting results. So thank you. Thanks everyone for your attention. I hope I've convinced you that this teleparallel gravity isn't a crazy theory.
Thank you, Jackson, for your interesting talk. So we have time for a couple of questions, comments. You can write on the chat, or we have one. Let me see. Francisco, you can ask him directly, please.
Thank you, Elias. And thank you, Jackson, for the nice lecture again.
Thank you.
And also thank you for clarifying this thing of the Bianchi identities at the beginning of your talk. I'm curious about the posteriors you have shown when comparing the lambda CDM model with these three different FFT functions. I don't know if you can go back to that slide.
Okay. At the very top, I think, right?
Yeah.
Sorry. Okay. So is
yeah.
F1.
Yeah, for example, yeah. So it is
12 horas.
It is very well known that when you consider the data from CMB, it is a clear anti-correlation between the amount of matter, omega m, and the H0 parameter. You can see there in the lambda CDM posterior, for instance.
Yes.
This is small. Once you include the CMB data, your posterior, your 2D posterior, shows an anti-correlation between these two parameters. And I'm curious about this following fact. When you consider your new gravitational framework, this anti-correlation seems to be reduced. In fact, I think that if you compute not the correlation matrix, but not the covariance matrix, but the correlation matrix, you're going to have some values indicating in these two parameters in particular that the anti-correlation is getting reduced. So I'm curious about you know what kind of physical mechanism this function f of t are inducing in the cosmological ground that are producing this kind of behavior in how these two parameters are correlated.
Yeah, I don't think so many studies have, I think a lot of these have been, just trying to find out more information about reasonable values of these new parameters. I mean, that would be something interesting, I think, to look at. I'm not aware of any studies that actually discuss this in any great detail, but it's an interesting observation, and I think this would be something interesting to have a look at.
Yes, the question is in the direction that probably if you want to work on this H0 tension, for instance, probably you want to know how are related each parameter in a cosmological setup, and having in mind which are the physical processes that can alleviate this tension. So that's my curiosity.
Yeah, I mean, again, I mean, if you're interested, we could definitely have a chat about doing this. But so far in the literature, I don't think anyone's actually discussed in detail the mechanism that has produced this. But it does seem to come out from the analysis. So there isn't really an answer from literature yet.
Okay.
Say it like that. I mean, I would say again. In teleparallel gravity, and specifically f of t, so f of t is not in a sense, okay, it's inspired by f of r, but it's not an analog of f of r. The analog would be f of tb. So we would expect novel physics to come out from f of t, and this is a specific example of one of them. So yeah, so why we don't know, we do expect new things to happen, let's say. So That's all that I can really say from what we know about f of t in this regime.
Okay. Thank you very much, Jackson.
Thank you.
Thank you. Anyone else? Okay, if not, I have one question that was sent to the website from Aram Aguilar. So the question reads, some advantage